Today we begin with a brain teaser. Is it possible to construct a function whose height at a given point x is equal to its slope at that same point x over the entire domain? In other words, is it possible to construct a function whose derivative is itself? In this lesson, we are going to discuss the possibility of such a function, but we are going to start by talking about logarithmic and exponential functions and how to take their derivatives. First, let's quickly review how log functions are used. Logarithms are written in the format log base a of b is equal to c, where a is the base, b is the argument, and c is the exponent. Writing log base a of b equals c is equivalent to writing a to the c equals b. For example, what does log base 3 of 9 equal? We can answer this by asking 3 raised to what power equals 9. Clearly, 3 squared equals 9, so log base 3 of 9 equals 2. The most common logarithmic function we use in calculus is the natural log, written ln. ln is equivalent to log base e. As a quick example, what is ln of 1 equal to? Remember that e is the base of all natural logs, and ask yourself, e, the base, raised to what power equals 1? The answer is 0. Now that we have refreshed our memories on how to use the natural log, we need to talk about its derivative. Fortunately, ln's derivative is surprisingly simple. The derivative of ln of x is equal to 1 over x. Let's use this to work out the derivative of the function f of x is equal to ln of x plus 3x. This function is a polynomial, so we look at each term individually. As we just said, the derivative of ln of x is 1 over x. And we know that the derivative of 3x is simply 3. So therefore, the derivative of f of x, so f prime of x, is equal to 1 over x plus 3. Now, what if we wanted to find the derivative of g of x is equal to the natural log of 3x plus 4? It is tempting to say that the derivative should be 1 over 3x plus 4. But because 3x plus 4 is a function within our function g of x, we must instead use the chain rule. Applied to the natural log, the chain rule tells us that the derivative of the natural log of u, where u is the internal function, is equal to 1 over u multiplied by the derivative of u. Let's use this formula now to find g prime of x in this problem. So u for this problem is going to be equal to 3x plus 4. That's our function inside the natural log. So then du, or du over dx, is going to be equal to the derivative of u, which will be 3. So therefore, the derivative of g of x, or g prime of x, is equal to the function, 1 over the function, so 1 over 3x plus 4, times the derivative of u. So times 3. We can then simplify this to be 3 over 3x plus 4. Let's work one more example before moving on. Find the derivative of the natural log of 4x squared plus 5x. To solve this derivative, we just need u, its derivative, and the chain rule formula. So in this problem, let's let u equal what is inside the natural log, so 4x squared plus 5x. We'll then take the derivative of this to get du over dx, which will be 8x plus 5. Now we can plug these into the formula. So we have that the derivative of ln of 4x squared plus 5x is equal to 1 over u, so 1 over 4x squared plus 5x, times du dx, so times 8x plus 5. We can simplify this into one fraction and get 8x plus 5 over 4x squared plus 5x. So the derivative of the natural log of 4x squared plus 5x is equal to 8x plus 5 over 4x squared plus 5x. Let's now talk about the natural exponential function. As you may have guessed from its name, the natural exponential function involves e, just like the natural log does. It is written e to the x, and its graph looks like this. The relationship between e to the x and the natural log of x can actually be shown graphically because they are each other's inverses, reflected across the line y equals x. Remember the brain teaser from the beginning of this video? It turns out that the natural exponential function has several important properties, one of which is that it is the only function whose derivative is itself. This is a fascinating fact that will help us greatly with derivatives of functions containing exponentials. But how can we be sure that it's true? Let's see if we can prove it now. We can start by writing the function as y equals e to the x. Now remember, we said that the natural exponential function is the inverse of the natural log. We will use this fact along with a special property of ln to modify our starting expression. First, let's take the natural log of both sides so that we have the ln of y is equal to the ln of e to the x. Can the ln of e to the x be simplified? Ask yourself, e, the base, raised to what power gives us e to the x? Obviously, e raised to x does. That means that the right side of the equation is equivalent to x. So we have the natural log of y is equal to x. The next step in this proof is a little bit sneaky, so follow along carefully. We are going to differentiate both sides with respect to x. Since y is a function, we need to treat the left side with the chain rule. Using the formula from earlier, this gives us 1 over y multiplied by the derivative of y with respect to x. The derivative of x on the right side gives us 1. To simplify this expression, multiply both sides by y. This will eliminate the fraction on the left and leave us with dy over dx is equal to y. We now have that the derivative of y with respect to x is y. That means that y equals e to the x does in fact have the special property of being its own derivative. We can also observe this fact graphically. Look at the graph of y equals e to the x and see that at height y equals 1, e to the x has a slope of 1. Similarly, at height y equals 2, e to the x has a slope of 2. And at height y equals 4, it of course has a slope of 4. Since e to the x is its own derivative, you can determine the derivative of f of x equals 4 times e to the x. To solve, we'll use the product rule. F prime will equal 4 times the derivative of e to the x plus the derivative of 4 times e to the x. So we have 4 times the derivative of e to the x is e to the x, plus the derivative of 4 is 0. 0 times e to the x is 0, so plus 0, which gives us that the derivative is simply 4e to the x. A lot of derivative problems involving the natural exponential function require the use of the chain rule, which by now you should be plenty familiar with. Whenever a function appears in the exponent above e, use the formula the derivative of e to the u is equal to e to the u times the derivative of u with respect to x. For example, we can find the derivative of e to the sine of x by using the chain rule. For this function, u is equal to sine of x. That means that the derivative of u, or du over dx, is equal to cosine of x. Plugging these into the chain rule, we'll get that the derivative of e to the sine of x is equal to e to the u, e to the sine of x, times du dx, so times cosine of x. The natural exponential function helps scientists model real-life phenomena like compound interest, population levels, and radioactive decay. Test your comprehension now with this practice problem. Biologists studied the population of horses on a certain wildlife reserve and found that it could be modeled closely with the function h of x is equal to e to the 1 over x plus 3 times the natural log of x, where x represents the number of years since the study began. What is the rate of change in this population? Pause the video now to find the solution on your own. I hope you gave it your best shot. The correct answer is h prime of x is equal to negative e to the 1 over x squared plus 3 over x. Let's work through the problem together now. We are given the function h of x is equal to e to the 1 over x plus 3 times the natural log of x. This models the population, and we are asked to find the rate of change in that population. This phrasing indicates that we need to take the derivative of h. The first term of h is e to the 1 over x, which we can differentiate using the chain rule. So if we're trying to find the derivative of e to the 1 over x, we can set u to be equal to 1 over x, which makes the derivative of u equal to negative 1 over x squared. So now we can use our chain rule formula, which tells us that we take e to the u, so e to the 1 over x, and multiply it by the derivative of u, so multiply it by negative 1 over x squared. We can further simplify this to be equal to negative e to the 1 over x squared. The second term, 3 ln of x, is easier to differentiate. Use the product rule to see that its derivative is simply 3 over x. So if we take the derivative of 3 ln of x, we'll take the derivative of 3, so d over dx of 3, times the natural log of x, and then add 3 times the derivative of the natural log of x. So the derivative of 3 is 0, multiplied by the natural log of x is still 0, plus 3 times the derivative of the natural log of x is 1 over x. And this will simplify to 3 over x, like we said before. So now we simply put these two terms together to get h prime of x, which is the rate of change in population. So h prime of x is equal to negative e to the 1 over x squared plus 3 over x. Now that we have gone over the natural log, the natural exponential function, and their derivatives, there are just a few more useful properties and applications for us to discuss. First, we can combine the properties of the natural log of x and e to the x to solve expressions with a variable in the exponent. For example, given the expression a to the x, where a is a positive real number and x is any real number, you can solve for x by using the formula a to the x is equal to e to the x times the natural log of a. For example, if we were given the function 2 to the x equals 128, we can solve for x using this formula. This equation can instead be expressed as e to the x times the natural log of 2 is equal to 128. From here, take the natural log of both sides to bring down the exponent. So if we take the natural log of the left side, our natural log and e will cancel each other out and we'll be left with just the exponent part. So x times the natural log of 2 is equal to the natural log of 128. From here, to solve for x, we can divide by the natural log of 2 on both sides. These will cancel out and we'll be left with x on the left side. So x is equal to the natural log of 128 divided by the natural log of 2. This solution, if you plug it into a calculator, can be simplified to x equals 7. A second application is taking the derivative of such an expression. Use the formula the derivative of a to the x is equal to a to the x times the natural log of a to do so. Following from the previous example, if we were to take the derivative of 2 to the x, This derivative formula tells us that the derivative is equal to 2 to the x times the natural log of 2. Of course, if we have a function with another function in the exponent, we can apply the chain rule to this derivative formula. That would give us the derivative of a to the u is equal to a to the u times the natural log of a times the derivative of u with respect to x. Using this in an example, we can take the derivative of a function like 2 to the 2x plus 1. We can do this by following the formula and applying the chain rule. So for this problem, we need to start by finding our u and our du. So u is equal to 2x plus 1, which means that du will be equal to 2. So now we can apply our formula. So the derivative of our function, 2 to the 2x plus 1, is equal to 2 to the 2x plus 1 times the natural log of 2 times the derivative of u, which is 2. We can then bring our 2 over to our other 2's and make this 2 to the 2x plus 2 times the natural log of 2. Finally, if you need to take the derivative of a logarithmic function whose base is not e, use the following formula. The derivative of log base a of x is equal to 1 over x times the natural log of a. Or if the argument of the logarithm is a function u, I'm sure you guessed it, apply the chain rule to this formula to get the derivative of log base a of the absolute value of u is equal to 1 over u times the natural log of a times the derivative of u with respect to x. Note that because u appears in the denominator, this formula can only be used when u does not equal 0. I hope that this lesson has helped you form a better understanding of the functions e to the x, ln of x, and finding their derivatives using the chain rule. Thanks for watching, and happy studying!